Hi, I'm presenting on optimal control as the mathematical foundation of macroeconomic theory. Our optimal control problem is associated with the Solow-Swan growth model as well as the Ramsey-Cass-Koopmans model. These are basically mathematically equivalent problems with some slight variable relabelings. These are all named after Nobel Prize economists and are historically very important because they gave rise to all modern macroeconomic theory. The subsequent models either build off of these foundational models or and provide further detail or provide interesting spin-offs for investigation. As such, this illustrates why the framework of optimal control theory is extremely important to economists. In particular, we will be investigating the Solow-Swan growth model. So the Solow-Swan growth optimal control problem is as follows. We'd like to maximize this functional, which represents a time integral, the total happiness level of society throughout all time, throughout the entire population. We would like to maximize the total happiness level of society as the benevolent societal or governmental planner by choosing a consumption trajectory that it contributes to happiness level. And notice how U is a function of C, and we're integrating over such function, where C of T is the controller variable trajectory, and K of T is the state variable, which corresponds to the capital accumulation equation from finance. And so this is the dynamics constraint. Observe the exponential factors. This characterizes time discounting, where we prioritize the present versus the future, as well as population growth here. So to solve such a system, we derive the first order conditions for optimality using the Hamiltonian method framework. In economics, usually the lambda costate variable is transformed as follows, which gives the present value Hamiltonian, which simplifies some of the algebra associated with infinite horizon optimal control problems. And skipping the algebra, taking the derivative of H with respect to the relevant quantities, we get the following first order conditions dynamical system. In practice, the utility function is log of C. And so plugging that in gives us the famous Ramsey-Cass-Koopmans dynamical system. And we get this, this result as follows. This is also known as the Keynes-Ramsey rule for optimal policy for consumption behavior, and a Nobel Prize winning result. As such, in an examination of such dynamical system, we perform a stability analysis. We take the determinant of the Jacobian at the stationary steady state condition, and we notice that the determinant is negative. As such, the Ramsey-Cass-Koopmans dynamical system is a saddle point dynamical system, and hence via the stable manifold theorem, there exists a curved line in phase space that passes through the equilibrium point, and all points on it ultimately are attracted to it, as indicated in the blue line in this illustration here. Everything gets attracted to the stable point on this saddle trajectory. So the stable manifold does indeed characterize the unique optimal trajectory, also known as the saddle trajectory. And so ultimately, to get a sense for this dynamical system, we provide an animation. To do such, we have to pick an example to illustrate. And so this involves picking an actual form of function f of k. This is the standard Cobbs-Douglas production function used in macroeconomics literature, also microeconomics literature as well. And we plug in the varying parameters into the system, and we get this system. Notice how the stationary point is the intersection of the dot k equals 0 locus and the dot c equals 0 locus right here. And some interesting points to consider. The stationary point here is not at the apex here, which maximizes consumption in perpetuity. This is because the first order conditions characterize optimality, and it is always possible to improve happiness level by putting consumption earlier on rather than later on. So you can sacrifice, you can move consumption around to increase happiness as such. Non-stable trajectories either blow up to k equals infinity, c equals 0, or c equals infinity, k equals 0. These do not reflect reality in our mathematical modeling. We would like to sustainable economic growth with no starving, so no c equals 0, and no bankruptcy where k equals 0. And as such, the economics wisdom takeaway from such a model is the c and k variables are defined to be normalized to total exponentially growing population. And so the stationary stable point equilibrium convergence means eventually the macroeconomic growth is more or less exponential, which strongly reflects empirical trends of many countries throughout history. Note, economic theorists tend to be more interested in these types of qualitative results analysis than specific numerical computational methods. As such, as a conclusion, this shows optimal control is a very powerful mathematical tool with a diverse array of applications. Thank you very much.